So, hello everyone. This is the second lecture, classification of intermolecular forces. So, in the last lecture, we discussed four forces of the nature: weak and strong forces, electromagnetic and gravitational forces. Followed by, we discussed the historical perspective of various intermolecular forces with timeline starting from 17th century to the 20th century. We also see few expressions of intermolecular potentials, intermolecular forces. Then we started with Lennard-Jones pair potential. We also did one example how to analyze the attractive as well as the repulsive nature of the LJ potential. In today's lecture, we will start with the classification of various intermolecular forces. What are different type of forces, starting from the strong intermolecular forces, weak intermolecular forces, short range intermolecular forces, long range intermolecular forces. Based on their origin of their forces, we will just see their expressions. Also, we will see few examples how to calculate those energy as well as the force term. So, to start with the classification of forces and pair potential. So, the very first thing comes is, if you want to go based on the opposite trend. So, you can have different classifications like attractive force and repulsive forces, short range and long range forces, strong and weak intermolecular interactions or forces, isotropic or directional forces. But here the issue comes, this classification has lot of ambiguity and confusing, because a force may fall into different categories. Also, the nature of force depends on the environment. So, a force may be the long range, but depending on the environmental condition, it may act as a short range force. It may be the strong force in the vacuum, but in the environment, in the solution or media, it may start acting like a weak forces. Strong force and weak force, isotropic and directional. So, it is better to classify the forces based on their physical or chemical origin. So, if you go by this, we can classify into three category. First one is the electrostatic interaction between two charged molecules. One example is the Coulomb interactions or Coulomb force. Second is the entropic, means depending on the movement of molecules like pressure. Yesterday we discussed about the gas law. The pressure apply the repulsive forces like osmotic pressure, thermal fluctuation, change in entropy because of change in temperature, because of the osmotic pressure. So, these falls under category of entropic forces. And third category is the quantum mechanical, and quantum mechanical origin includes your covalent or chemical bonding, van der Waals interactions, dispersion forces, acid base, charge transfer interaction, and the repulsive steric forces. So, we will see a few examples from the each category: electrostatic, entropic and the quantum mechanical forces. So, common type of interaction which we typically see in biological systems or any chemical system includes the covalent interaction, ion-ion or charge-charge interactions, then charge dipole interaction, dipole-dipole interaction, charge nonpolar interaction, dipole nonpolar interaction, nonpolar, this is also known as hydrophobic interaction, and hydrogen bonding. These are the few important common type of interactions, and especially if you see in biological system, many of these interactions operate simultaneously. If you take the example of DNA, it simultaneously have covalent linkage, always the hydrogen bonds. If you go for proteins, it has many. It has a start with the covalent dipeptide linkage, followed by the hydrogen bond. It has hydrophobic, also it has disulfide. So, if you just see, typically for biological systems, many of these interactions operate simultaneously. So, first we will start with the strong intermolecular forces. So, we can say one is the chemical force or chemical bond, other is the physical bond. So, chemical bond means it is typically covalent interaction, and physical bond, it includes the Coulomb forces, and different classification may be ion-ion or charge-charge, ion-dipole, dipole-dipole, and dipole-induced dipole interactions. So, this is one representation of covalent linkage in water molecule. There are two hydrogen atom, one oxygen atom, and sharing of this electron between oxygen and hydrogen results in the formation of covalent line. This is one amino acid where we can see due to the partial charge on the amine group and carboxylic group, there is a formation of dipole. So, this is the one example of the dipole formation, and this is one example of the chemical bond or the covalent bond. If you want to classify these two physical and chemical bonds, the chemical bonds, as you know, this covalent, this is highly oriented and well directional. It is a result of electron share between the atoms, and this is very short range force. But at the same time, if you just see the physical bonds, they are long range forces. Here atom need not directly come into contact because they are the long range forces. At the same time, they lack the specificity and the orientation because they are not closely attached to each other like the covalent bond. The orientation is not fixed for the physical interactions. So, we will start with the covalent bond first. So, covalent bond, it is very well known to all of you. This is formed by the sharing of electron between two atoms which are available or present in the valence shell of the atom, okay, or you can say depending on the atomic valency of two atoms, the sharing of electron takes place and the covalent bond formation occurs. This is very short range force, the typical 0.1 to 0.2 nanometer. So, this range is in the order of atomic distance or subatomic level, but its strength or potential is very high. It is very strong bond. Strong bond, its value lies between 200 to 800 kilojoule per mole, and apart from that, it gives specificity, means specific interaction between two atoms depending on their valency. Of course, stoichiometry, because it is sharing a particular pair of electron. So, it may be the single bond covalent, double bond or triple bond, and of course, when it is particular bonded, it is going to control the directionality after the bonding. So, I have listed a few example of this. If you just go triple bond, double bond, so of course, obviously, if you go for the triple bond, it is going to have more strength as compared to the double bond and single bond. So, if you just see the whole range, it starts from the close to 200 to the 870 or 800. So, its value is starting from 150 and it is going to the 870. So, this is very strong bond, the covalent interaction. Next one is the physical bond. So, which as I told it, first it is a long range force. One example is the Coulomb force, and as it is a long force, it acts between unbounded discrete atoms and molecules. So, I will start with one example of this physical bond or electrostatic interaction. So, if you just see, this is two bacteria. In one case it is having a cell wall, in other case it is having a fibrillal or spiked cell wall. Now, in which case it will have more surface charge. So, we found that the electrical potential at the surface of smooth surface is higher as compared to the surface with the fibrillar one or the spiked one. So, it says that the electrical potential is also a function of the distance as well as the whatever the surface structure is there, it is going to affect the physical or electrostatic interactions. Now, how this charge is coming on the surface to have the electrostatic interaction? So, there are two main mechanisms. One is the all the molecules or atom or compounds have a surface functional group. So, if there is any dissociation or association of surface groups, it results in generation of either positive or negative charge on the surface. The other mechanism is it is coming from the environment or surrounding. It is binding with some excess of the either anion or cation. So, whatever group is present on the surface, it is going to have the similar charge. It may have the positive charge, it may have the negative charge. So, these are the two main mechanism how the electric charge are applied on the surface. I have listed a few examples like oxide surface layer on metal and non-metallic elements. So, oxides obviously it will be the negatively charged. If you look at the biomacromolecules, it is going to have different charge: carboxylic group, amine group, phosphate group, sulfonate group and imidazole group. So, depending on this functional group, they are going to occupy the different charge. And of course, this if there is some salt solution and salts are adsorbed on the surface, so depending on the charge of the salt, the surface is going to have the different charge. So, once you are having a charged surface, how this electrostatic interaction works. So, let us say you are having a charged molecule which is having the charge of q1 at a distance of r. The electrical field is defined as q1 upon 4 pi epsilon naught epsilon into r square. So, it means the field is inversely proportional to the distance. E1 is inversely proportional to the r square, and also it is inversely proportional to the dielectric constant of the medium, inversely proportional to dielectric constant of the medium. So, this is one atom at a distance of r, this is the field. Now, there are two atoms, one is having charge q1, other is having the charge q2. So, once it is interacting with this q2, so force will be q2 into E1. So, if you put E1 from this expression 1 here, so it will be like q1 q2 4 pi epsilon naught epsilon into r square. This much is the force applied when two charged molecules are interacting, and this is also known as the Coulomb's equation or Coulomb's law. If the force is known to you, we can always calculate the potential. Potential is the, if you integrate the force, you will get the potential. Other way, if you differentiate the potential, you will get the force. So, if you integrate, so it is coming out to be q1 q2 4 pi epsilon naught epsilon into r. Now, as we know, q is directly related with the charge density into the charge on the electron. So Q1 you can write Q1 is Z1 into E1. E1 means you can write only E. Similarly Q2 will be Z2 into E. So you can write Z1 Z2 E square upon 4 pi epsilon naught epsilon R. So this is the electrical field or force, and this is the energy or the potential. Now we will just see one example of NaCl. Na positive charge, Cl is negative charge. They are coming in the contact and forming the NaCl. So can we calculate what is the interaction energy or what is the potential? So the formula is very simple, Z1 Z2 E square upon 4 pi epsilon naught epsilon into R. So Z1 will be, let us take this. So here Z1 will be plus 1 and Z2 will be minus 1. If it is calcium, then Z1 will be plus 2. So here if you put E electron charge density 1.602 into 10 to the power minus 19 and epsilon naught is this. So here we are considering, let's consider in the vacuum. Vacuum means epsilon is equal to 1. So it's coming out to be 8.4 into 10 to the power minus 19 joule. As we discussed in the last class, energy can always be converted in terms of thermal energy. So it is coming out to be 200 kT. So if you compare this value of thermal energy with the covalent linkage, it is found to be comparable. So we can say the Coulomb interaction or Coulomb forces are comparably stronger as the covalent interactions. Here R value will be sum of the two ionic radii Na plus and Cl minus, its value is 0.276. So if you put plus 1 minus 1 E square 4 pi epsilon naught is here, epsilon 1 and R is 0.276, we will get the interaction potential as 200 kT. Now from this, let us see what should be the distance when this potential or Coulomb energy will fall below the 1 kT. So if you put here WR is equal to 1 kT and we will calculate the value of R from this expression. So we will get the value of R is equal to 56 nanometer. So what it suggests, it is a long distance interaction. If you remember, for the covalent interaction, it acts at the atomic level, or you can say subatomic level 0.1 to 0.2 nanometer, but it is acting up to the scale of in the range of 50 to 60 nanometer. So it is a long range force, but at the same time, if it is interaction between two charged molecule, positive and negatively charged molecule, its strength or the potential is comparable to the covalent interaction. Now one more thing we can calculate from this. If you want to break an ionic bond, how much force will be required to break the ionic bond? So if you want to calculate A of R, you can simply calculate WR upon R. So WR is how much it was there? Minus 8.4 10 to the power minus 19 and R is 0.276 to the power 9. So this will be coming out to be close to 3 nanonewton. So here again it says if you want to break the ionic bond, you require this much of the force. Again this is comparable to the strength of the covalent linkage. So what we see here is the Coulomb interaction, particularly between the charged molecules, and its strength is found to be comparable to the covalent linkage, but it is a long range force. Now, let us say there is only single ion in the vacuum or in the medium, and it is as a single ion, it is not interacting, but still it has an electrical free energy associated with it, and that is known as the Born or Solvation energy of an ion. Even there is a single ion in either in vacuum or medium, even it is not interacting with any other ion, but still it possesses an electrostatic free energy, that is known as the Born or Solvation energy. So, let us say you are having a molecule which have the Q and its energy is increasing to the dq. So, we can simply calculate from the dw as, if you remember, q1 q2 4 pi epsilon naught epsilon into r. So, here q1 will be q and q2 will be dq 4 pi epsilon naught epsilon r. So, this is simply the called the Born energy, means electrostatic free energy of a single ion, it is the Born energy. And if you want to integrate it, you can calculate the total free energy if you want to integrate from the 0 to q. This is very simple integration. So, we will end up with this will be the q square upon 2, it is coming to the q square upon 2. So, we will have q square upon 8 pi epsilon naught epsilon a, and q as we discussed, q you can write q is equal to z into e, so z into e square upon 8 pi epsilon naught epsilon upon a. So, this is total free energy or the bond energy, and this of a single ion. So, we here will see one very interesting thing based on the intermolecular interaction, especially the Coulomb interaction. Can we relate this intermolecular interaction with the a physical or chemical property? So, we are considering the solubility. So, can we relate or you can say, can we predict the solubility of ions based on the intermolecular interactions? So, here again we are going to take the same example of NaCl. So, for NaCl, if you remember, this distance or interatomic distance was 0.276 nanometer. So, total free energy or Born energy, you can Z1 Z2 e square upon 4 pi epsilon naught epsilon into r. Okay. Now, here we are considering a medium, the dielectric constant is 78. So, 78 means it is a water. We are considering in the water. So, we can calculate the value of delta mu, both are having Z1 is 1, Z2 is minus 1. So, it will be simply E square upon 4 pi epsilon naught epsilon into interatomic distance between Na and Cl, it is 0.276, and solubility is given as Xs as e to the power minus delta mu upon kT. So, if you put all the value here, we will be able to calculate the value of Xs, that is the molar solubility, that is the molar solubility. And if you calculate here, then value of Xs is coming to be, we are calculating at T is equal to, K is the Boltzmann constant at T at 298, and its value will coming out to be 0.075. It is very close to the experimental value of Xs is 0.11. So, the predicted value is coming very close to the experimental value. So, we can say this intermolecular interaction between these two molecules can be directly related to the solubility. Now, if we just relate this interatomic distance and dielectric constant. So, we can say solubility or log of solubility is inversely proportional to the dielectric constant as well as the interatomic distance. Now, for the same molecule, what we are going to do is we are going to change the dielectric constant. It means the NaCl, if you are going to put in the different medium a different dielectric constant. So, if you plot between log of xs versus 1 upon epsilon, we should get a straight line. And if you can get the straight line, so you should be able to also calculate the, you can say back calculate the what is the interatomic distance between A plus and A, or you can say Na plus and Cl minus. So, this is the log plot, this is the log of xs, so 1 upon epsilon. It is starting from origin is starting from the infinite, and this is NaCl. You can see different medium, methyl formamide, water, ethylene glycol, ethanol, methanol, butanol, pentanol, in different solvent with different dielectric constant. We have a linear. So, as expected, we are having a linear graph, and its slope is coming to the minus 167. Now, from here we will try to back calculate what is the inter-ionic spacing at temperature 298 K, 25 degrees centigrade. So, once this slope is known to you, then slope will be equal to the E square upon 4 pi epsilon naught r kt. So, the slope is equal to the E square upon 4 pi epsilon naught k into t. Of course, this is the r which we are going to calculate. These are the constants, all value are known to you, you can recalculate the value of r, and if you calculate from this slope, it is coming out to be 0.34. And if you remember, if you simply sum up the ionic radii of Na plus Cl, it is coming to be 0.276 nanometer. So, if you go for the back calculation, the interatomic spacing from the solubility data, it is still very much agreeable. So, what is discussed here is from the intermolecular interactions, we will be able to calculate the physical property like solubility, and even the solubility is known to you, you should be able to calculate the interatomic spacing. So, from the charge now we will see the dipole-dipole interaction. Dipoles are generated by the separation of opposite charges in a system, giving a net charge to the system. So, this dipole may be a permanent dipole, it may be the induced dipole. Like in typical example of HCl, they are already bonded together, but H may have the partial positive charge, Cl may have the partial negative charge. So, it is going to have some sort of dipole, and this is called the dipole or permanent polar molecule. But the other example is the dipoles are generated depending on the environment. Or medium, like one amino acid is the glycine, it is not having any dipole, but if you put in the medium, in the aqueous medium, or in the water, it is going to have the amine group is going to have the partial positive charge, and carboxyl group going to have the negative charge. So, this is called the induced dipole. So, if there are two dipoles, again there will be the interaction between the dipole-dipole. So, dipole moment of a polar molecule is defined as mu is equal to q into L, where q is the charge one is the plus q, other is minus q, and L is the distance between two charged molecule, plus minus, this is the L. So, if you are having, let us say, two molecules which is having one electron charge, they are separated by the L is 1 nanometer. So, we can simply calculate that dipole moment will be E electron charge into 0.1 nanometer. We can calculate in the meter, it is coming out to be 1.6 into 10 to the power minus 29 Coulomb into meter. So, typically if you see the dipole, it is reported in terms of Debye length. So, Debye length is defined as 2 unit charge are separated at a distance of 0.02 nanometer. So, if you calculate the dipole moment of the 2 unit charge molecules or ions at a distance of 0.02 nanometers, so that is known as the 1 Debye. So, if you divide by this, you will get the 4.8 Debye. So, typically whenever we will see the dipole moments are always reported in the unit of Debye, and Debye is defined as dipole moment between two unit charge molecule placed at a distance of 0.02 nanometer. Similar to the Born or Solvation energy, dipoles also have the dipole self energy. This is very much similar to the Born energy. So, we will simply write here similar expression as we discussed for the Born or the Solvation energy of ions. It will be q square upon 4 pi epsilon naught epsilon L. Now, here we are considering L is equal to twice of the radius of a particle. So, we can write 8 pi epsilon naught epsilon into A. Again this q you can write in terms of dipole moment, q is equal to q square is equal to u square upon L square. So, this will be u square upon 4 pi epsilon naught epsilon into L cube. So, this is the expression of the dipole self energy. Now, we are having the ion and dipole interaction of charged molecules and atom like sodium, and other is the polar molecule water. So, here we are having a charged molecule, let us say sodium, this is polar molecule water. They are placed, linear distance is the r, but if you just see the distance at the polar, let us say we are defining A, here defining C, we are defining B. The distance from here is AC and distance from here is AB. Now, if you want to calculate the potential, or you can say ion dipole potential, or you can say total interaction energy. So, we will write q into q, this charge is q, they are having the charge of q, 4 pi epsilon naught epsilon. Now, what will be the distance? For this case, distance will be the AB. So, in one case 1 upon AB, 1 upon AC. Now, this AC and AB can be converted or written in terms of r, as this angle is known to us, and this length will be 1 upon 2 L, half of the distance between two, and this is theta. So, this will be the simply 1 by 2 L cos theta. So, value of AC we can write r plus 1 by 2 L cos theta. Similarly, for AB we will be writing r minus, this is coming towards minus side, r minus 1 by 2 L cos theta. So, if you put the value here, so WR will get minus q small q 4 pi epsilon naught epsilon L cos theta divided by r square minus 1 upon 4 L square cos square theta. We can simplify it and you will get the value minus q into dipole moment, q into L is equal to u cos theta upon 4 pi epsilon naught epsilon into r square. So, we are neglecting this term. So, here u is coming q into L. So, how it is interacting? Charge molecule, dipole moment, angle the theta, 4 pi epsilon naught epsilon, and distance from here to here is the linear distance r. So, in this way we should be able to calculate the total interaction energy or interaction potential between the ion and the dipole molecules. Now, we are going to have two dipole. Two dipole means both are going to have certain angles. So, it will be the function of r, it will be the function of theta 1, it will be the function of theta, and another angle phi. So, it will be the function of the 4. So, dipole interactions are analogous to the interaction of magnets, and for dipole with moment, of course, they are going to have this separate moment mu 1 and mu 2 separated by a distance r. The interaction energy of dipole moment, it will be the function of r as well as the both the angles and this new angle psi. So, we can write u1 u2 upon 4 pi epsilon naught epsilon r cube. In the previous expression, if you just see this r cube. Now, this is the function of cos theta 1, cos theta 2, sin theta 1, sin theta 2, and cos phi. So, this is the expression of dipole interactions. So, here what we are seeing is u, one r is coming from here, other r is coming from here, and one r was already there. So, it is a r cube, u1 u2 4 pi epsilon naught epsilon into r cube, because q, if you just remember, q is equal to u upon L. So, there will be r cube, r was already there, one r is coming from here, one r is coming from here. So, this will be the r cube plus, of course, this is again two different angles, cos theta 1, cos theta 2 minus sin theta 1, sin theta 2, and cos phi. Now, as this cos theta is coming, so maximum value of cos theta will be at the 0. So, if you put this value at 0, so this will be 2 u1, 2 is coming from here, u1 u2 upon 4 pi epsilon naught epsilon into r cube. So, this is the maximum attraction occurs when dipoles are lying in the line. In the line means theta is equal to 0. So, this is the expression, or this is the way to calculate the energy of interaction between dipole and dipole. So, these are the some strong intermolecular forces. Now, we will go to the van der Waals forces. So, first we will see van der Waals dispersion force. If you just see any molecules, it is not charged, but still it experiences some sort of interactions. Even it is helium, inert gas, still they feel some sort of intermolecular interactions, and that interaction, which is irrespective of the surface charge, it acts between all kinds of molecule, including the neutral molecules, that is called as dispersion force, or you can say London dispersion force. Also, it is called electrodynamic force or induced dipole forces. So, what it says, it is not the charge, it is a neutral molecule, but still it will experiencing some sort of intermolecular interactions, that is known as the van der Waals dispersion forces, and this plays very crucial role in the physical adsorption, in the surface tension, the adhesion, the weighting, flocculation of the particles, structure of the condensed macromolecules like the proteins and polymers, and of course also it governs the property of gas, liquid and solid and thin film. So, this dispersion force play very important role. So, key feature of this van der Waals dispersion force is it is a long range force. It can act as close as 0.2 nanometer to larger than the 10 nanometer distance. It brings molecules together, it causes mutually alignment and reorient the molecules, like you will see in case of proteins, in case of thin films, and this is non-additive in nature. It means the interaction between two molecules will be affected by the presence of other surrounding molecules. So, total interaction is non-additive in nature. So, this potential, this London dispersion potential is expressed at minus C dispersion upon r to the power 6. So, this is for the neutral molecules. Now, if you are seeing the van der Waals dispersion force between the polar molecules, now the polar molecules is going to have three different kind of induction, orientation and dispersion. So, the constant term will be the sum of C induction, C orientation and C dispersion divided by the intermolecular distance r to the power 6. So, this way we calculate the van der Waals dispersion force. Now, it is this force may be mostly in the attractive in the nature, but if you just see if you remember the last class also we discussed apart from the attraction there always be the repulsive force. That is why it balances. If it comes very closer there will be repulsion, if it goes far away there will be attraction. That is why the system lives in the equilibrium. So, the repulsive potential here is known as the steric or exchange or hardcore or bond repulsion. So, we consider one atom or molecule as a hard shell and other is the hard shell. When they come very close, so electron cloud they repel each other. So, that is exactly known as the repulsive potential or you can say steric repulsion, and this is expressed at the as a function of sigma and r. Sigma is the size of that particular molecule, size of molecules or atoms. See the size of atoms, and r is the distance, interatomic distance. So, if you remember, if we combine both attractive as well as the repulsive forces together, so we are going to have this pair potential or you can say Lennard-Jones pair potential. So, it says it is having both attractive terms as well as the repulsive terms, and which can be further simplified by in terms of size of the molecules or size of the atom divided by the interatomic distance. So, this will be the 4 psi sigma upon r to the power 12 minus sigma upon r to the power 6. Now, if you want to calculate as we did in the last class, if you want to calculate WR minima, then you have to calculate dW upon dr is equal to 0. So, in this way we will be able to calculate at what value of r we are going to have system will be in the equilibrium. WR minimum means it is in the equilibrium. So, if you calculate simply, we will get WR is equal to minima at R is equal to 2 to the power 1 by 6 sigma. So, it means at 1.12 times of the size of the molecules, your system is two molecules are going to be at the equilibrium 1.12 sigma. If you remember, in the previous exercise also we got the same value of, this was the ratio of R E upon R naught, that was the 1.12. So, here we discussed, started from the covalent interactions, then Coulomb interaction between ion-ion, then ion-dipole, then dipole-dipole. Then we discussed some non-electrostatic forces like London dispersion force, then steric repulsion, and if you combine them, it is like total intermolecular polar potential. So, other forces are, one is the hydrogen bonds. So, this is the weak bonds which arise between the two molecules involving the hydrogen atoms. So, if there is a hydrogen atom, there is a possibility of formation of hydrogen bonds, and these hydrogen bonds may be the intermolecular or intramolecular. And one unique example is the water. See, water is a very small molecule, but because of the presence of hydrogen bond, it has very high melting point, very high boiling point. It means you can say, depending on this intermolecular interactions, or you can say hydrogen bond, its properties is directly related. Its melting point, its boiling point, its latent heat. So, all the property are directly related with this hydrogen bond, and hydrogen bonds is formed between the electronegative atoms and hydrogen positive charge hydrogen atoms, electron O, N, F and Cl, these are few. And the typical strength of this, as we told, it is a weak bond, it varies between 10 to the 40 kilojoule per mole. So, interaction energy for hydrogen bond formation is calculated. So, if you just see how it is forming, hydrogen bond is OH negative. So, it is sort of ion-dipole or dipole-dipole interaction. So, the interaction energy is calculated in the similar way, charge on the hydrogen plus dipole moment cos theta upon 4 pi epsilon naught epsilon into R square. So, this is very similar interaction potential as we discussed for the ion-dipole interactions. Now, I have this is one example of TiP5P water molecule. This is modeled water molecules which is having one oxygen and two hydrogen atoms. So, here let us consider QH is charge on the hydrogen is 0.24 electron and a value of Al is 0.096 nanometer. So, based on that we want to calculate what will be the interaction energy. So, to calculate the interaction energy, first we need to know value of R. So, as you remember, R will be the 1 by 2 L cos theta plus interatomic distance between O minus and S plus molecule. So, that this value is the 0.176. So, R is coming out to be 0.226 nanometer. Now, also we need the value of dipole moment of water. The dipole moment of water is 1.5 d. D is the dBi, as I discussed. The dipole moment is reported in terms of d. So, d is here. So, if you put the value of d, we are going to have dipole moment of water 5 into 10 to the power minus 20 Coulomb into meter. Now, let us consider in the vacuum. For vacuum, we are taking epsilon as 1 and as we have taken this linear distance r, so we are putting theta is equal to 0. So, if you calculate the interaction potential or interaction energy in the water molecule, it is coming out to be QH 0.24 electron, U 5 into 10 to the power minus 20 cos theta, theta is equal to 0, 4 pi epsilon naught, epsilon is we are taking 1 in the vacuum, and R we have calculated 0.226 nanometer. So, it is coming out to be 3.4 10 to the power minus 20 joule, and if you convert in terms of kilojoule per mole, so it is coming to be 20.4 kilojoule per mole. So, this is falling in the same range as we discussed. The hydrogen bond energy falls in the range of 10 to 40 kilojoule per mole. So, this is like a ion dipole interaction, or you can say dipole-dipole interaction exists between electronegative and the hydrogen atoms. So, next we will see the hydrophobic interactions. So, if you are having the interaction between the water and the nonpolar molecules, so or you can say inert molecule, they are immiscible, and this interaction is basically coming through the change in entropy, or you can say this is the entropic nature, and as this interaction is taking place with involving the nonpolar molecules, this is known as the hydrophobic effect. So, because of the presence of nonpolar molecules, the strong interaction between the hydrophobic molecules and surface in water. So, hydrophobic molecules try to come closer, and the water molecule comes on the surface and it surrounds it. So, this leads to the change in the entropy of the system. That is why this hydrophobic interaction is governed by the entropic driven, and this is effective range is 1.5 to 2 nanometer. So, hydrophobic polar pair potential is defined by it is exponentially proportional to the distance and directly proportional to the sigma exponentially proportional to the r. Sigma is the size of molecule, r is the distance with interatomic distance. So, the WH, a hydrophobic pair potential, is directly proportional to the sigma and exponentially proportional to the r. This is kilojoule per mole. So, it is defined as minus 20 sigma e to the power minus r minus sigma upon dH, and dH is the characteristic hydrophobic decay length, and a typical order is about 1 nanometer. The kilojoule per mole can also be rewritten in terms of thermal energy kT. K is the Boltzmann constant here again. Now, let us say we are considering R is equal to sigma. If you consider R is equal to sigma, means we are going to have dimerization. So, this potential is called the free energy of dimerization. So, delta G dimerization is the WH at the sigma. So, it is will be this term will be 1. So, we are going to have minus 20 sigma kilojoule per mole. This is the free energy of dimerization. So, free energy of dimerization is known for many molecules. We will just see one example here. Delta G dimerization or dimer for cyclohexane. For cyclohexane, the value of sigma is 0.57 nanometer. So, if you put the value of 0.57 nanometer, delta G dimerization is coming out to be minus 11.4. It is very close to that value minus 11.3 or so. So, we can see using this very simple pair potential expression, we are able to calculate the free energy of dimerization, or you can say the pair potential. As we discussed earlier also, once this potential is known to you, you can always calculate the force. The force is always minus dW upon dr, and if you want to calculate the force at r is equal to sigma, it is coming out to be 3 into minus 10 to the power minus 11 sigma nanometer at 298 K. So, let us take sigma is equal to 0.5 nanometer. If we take 0.5, that is hydrophobic force value will be close to 15 piconewton. So, this is the strength of the hydrophobic interactions if the size of molecules or the sigma value is 0.5 nanometer. Now, if you want to see at what value of R this hydrophobic pair potential WR will be 1 kT or less than 1 kT. So, from this expression we can easily calculate, let us say take sigma is equal to 0.5 nanometer. So, if you sigma take dH is already 1. So, we should be able to calculate at what value of R this hydrophobic polar pair potential value will be less than 1 kT or equal to the 1 kT, and it is, if you calculate, it will come out to be in the range of 1.5 to 2 nanometer. That is why we discussed the effective range of hydrophobic interaction is in between 1.5 to 2 nanometer. So, what we discussed today is we started from the classification of various forces. So, first we started with the classification based on the opposite nature: attractive, repulsive, weak and strong, directional, isotropic, short range and long range forces. But what we observed is this classification has the ambiguity. So, we started based on the origin of the forces. So, it was the electrostatic, then entropic forces and the quantum mechanical. So, we started with the strong intermolecular interaction, covalent interaction, then electrostatic interaction between charge ion and dipole and dipole interactions. We also saw the few examples how this interaction or intermolecular interaction can define the physical property, like we see the solubility of the NaCl, and also from the solubility can we calculate the interatomic distance. Then from the solubility data, then we discuss the some physical interactions like van der Waals dispersion force and steric repulsion. We combine them, then we got this pair potential, specifically Lennard-Jones pair potential. Then followed by we just saw the non-polar or hydrophobic interactions or electronegative and hydrogen ion interaction like a hydrogen bond, their strength and the effective range. So, I conclude this lecture here.